Now we come back to the state where actually what kind of equation of state we could use for non-ideal gas. One of the example that we could use is what we call as virial equation of state. Virial equation of state, it is a primarily mathematics motivated equation of state, and mainly it is actually developed from the ideal gas equation, okay, where B, C and D, where these terms C and D are considered as material dependent constant. It is a function of temperature, and it is second, third and fourth virial coefficient. So this is the first virial coefficient, second, third and fourth. What if B, C and D's values are 0? Okay, so if let's say you start substitute, this is 0, this is 0, this is 0, so you will just immediately get PV equals to RT. Okay, and V prime, molar, specific molar volume is V over N, so actually you just get PV equals to nRT. So the virial equation of state, okay, is what we call as one of the non-ideal gas equation of state, and it is used to estimate the virial coefficient which are not well developed except the second. Okay, which are not well developed except the second one. What does it mean by the second one? So this is the second one. So the C and D are not well developed. So they just use truncated after B. Okay, so we only use this particular equation in order for us to estimate the gas behavior, okay, especially the mixtures at non-ideal gas situation. Where B here, okay, you can further calculate using this equation, RTC divided by PC. And TC and PC are the critical temperature and pressure, and the term B0 and B1 is considered as another expression which will be given in the next slide. PV equals RT or equals to 1 plus B over V. So this is actually the truncated virial equation of state. Okay, why it is truncated? Because it's only stopped at B, right? And then after that, you have the expression for B. So B is given as RTC over PC, B0 plus omega times B1. So this is one of the equation. And after that, after that, you have B0, which basically can be obtained by using this particular equation. Okay. And then you have the term of TR, which what we call as a reduced temperature. Okay. And then this is also TR, which is also another reduced temperature. B1, we can use this expression. And then the pizza centric factor, what the heck is this? So we're going to look at the next slide. What is actually pizza centric factor? But before that, I think I'm going to share with you what does it mean by reduced temperature. So these are the corrected or normalized condition of temperature, pressure, and volume. Okay, so in order for us to calculate the reduced parameters so that we can use the equation, is simply like putting TR equals to T over critical temperature. T is the temperature that we are actually looking at. We are actually assessing the conditions, and TC is something that you can obtain from the phase diagram itself. Similarly with PR, which is reduced pressure, as well as reduced volume. Everything that we calculate is actually the actual condition given divided by the critical temperature, critical pressure, or critical volume at that particular condition of critical points. Okay, so we divided by that. This is where actually we got the reduced temperature, the reduced parameters. So if we want to look at the non-ideal gas equation of state, this is also given as there is another term that we need to know, which is what we call as pizza eccentric factor. So pizza eccentric factor is something that the chemist has basically trying to evaluate this. I do not know how basically they could evaluate these parameters through certain kind of polarity and shape of the molecule, and therefore these particular values are already given. Okay, so you can refer to the textbook. Example as in Felder and Rousseau, elements of principle of chemical engineering. Okay, and then you'll be able to see that different kind of molecules will have different eccentric factor. So you just pick that number and substitute into the equation, and you'll be able to get, when you substitute this number, then you'll be able to use the virial equation of state. Okay. So let's have a look at another video, okay, when I'm going to describe about another equation that we can use, which is what we call as cubic equation of state.